Teaspoon ventilation. Developers often say if we cannot get out of the basements quickly, the project tanks. And we're looking to basically not install so many things so that we can save money. But the reality is that there are many trades trying to work on top of each other, all of them in a panic to keep up with the builder's program. The builder, though, he's got his own concerns, or they've got their own concerns, and they're not going to be able to assist us too much. They're going to basically set the stage for the mechanical engineer to resolve the duct clashes that are occurring. And there's lots of reasons for clash. Very large ducts, clashes with sprinkler systems, locations of fans, prevention of running man sign visibility, lots of pipework to coordinate with. There's clashes and damages to ductwork. There are new systems that tempt us with their ease, but they often have extra systems that need to be supplied, new plant rooms in unusual locations, or there's discharge issues or duct height issues. Then we get to the roof where we need to discharge, and we find that we've got the route to the roof to consider, the risers, and all the time we need to satisfy our certifier that we are compliant. In the back of your mind, there's one thing running around. How do I make a profit out of all of this? We believe we have the answer, but it comes through resolving the problem. The problem is that most ventilation codes require that all of the car park is well ventilated. And this particular rule says 90% of the car park shall be within 3 metres of the shortest path between supply and exhaust. So there's massive duct expense. The ducts and their routes are extensive throughout the car park. There's lots of coordination effort, and there's risers to coordinate with the structure early on. There are plant rooms that we haven't planned for yet. And of course, there are large ducts that need to connect to outside. And as we go up the building, we're left with the legacy of these design decisions. And thankfully, in this instance, the risers are not backing onto noise-sensitive areas, but that can often be the case. And then when we get to the roof with these fire-rated risers, we need to deal with the roof real estate, which is becoming more and more valuable in this era. At the heart of it is the need to minimize carbon monoxide concentrations to 60 parts per million. How do we do that and keep all of our work together? The code says, the deemed to satisfy code, is that you plot all of these air paths, and that requires ducts that run the perimeter. Convention says that we need to have a well-maintained air environment. So ducts run the length of the laneways to ensure that there are no dead spots. That's the yellow duct that we see highlighted there. Sometimes too, we've got rules such as only so much air can be provided by a supply air outlet, or only so much space can be served by a supply air system. All of these draconian rules reflect an era when we didn't have the design tools we have today, or the techniques. Here we've got an example on screen of a jet fan. But the way the code treats the jet fan is that air is like a tennis ball and it bounces off the wall like this. There's one fundamental misunderstanding here. Tennis balls work on a different momentum. The tennis ball is much heavier than the air it passes through, whereas the air that we blow is the same. One of the things that we must recognise is that combustion engines have the same emission rates now as they did 30 years ago, but they warm up quickly. And this here is the saving grace, and it's found in many ventilation codes. You can do what you want as long as you can demonstrate that the carbon monoxide concentration is minimal. And this works well for rectangular car parks, but once you start introducing H patterns in structure, then suddenly it becomes very difficult. Look at this design. There's a big supply air plenum up across the top, and then in peach colour, you see all of the ductwork. In this design, we see the shopping centre, which has got a lot of H patterns, and it's extremely difficult to establish those rules without extensive ductwork. So the more unusual the geometry, the more difficult and expensive the car park becomes. Keep in mind, we only need to follow this particular rule to achieve dilution. But without following that N4 rule, we end up having to run ducts along the length and the perimeter of the car park. This means that we influence and hit just about every service going. We have to manage head heights above disabled car parks, which can be difficult. We have to be able to locate fan rooms in such a place that we can service those duct systems. And hence the expenses build. And we end up with large ductwork systems travelling right throughout the building. And of course, we need to deal with the risers and the plant rooms that come along with that. So, what is the solution or the response? Firstly, it's the teaspoon technique, whereby we create a swirl. So this is in plan view of a small car park. We create a swirl around the car park. And just as when we stir coffee, we're only moving a small amount of coffee, and yet the whole teacup is diluted and mixed. That's the same principle here. The second technique is to add a coander outlet, which is a means of establishing that the back wall becomes part of the ductwork system. We're using the shell of the car park as a duct to move and create airflow patterns throughout the building. And the third tactic is what we call exit path focus. So before we leave coander outlets, this is one of our first designs, and you can see there the grill discharging at high velocity along the soffits and the walls. Coming back to the exit path focus, by using the exit path carefully, we're able to remove supply air fan systems and establish that swirl. And we begin to think of the car park not just in the plan view for one plan, but in a stack of floors. And in that manner, we're able to seriously diminish the amount of ductwork that's required throughout the space. At the heart of it all is the coander principle, which is the principle that when air is blown close to a surface, it will attach. And in its attachment, the airflow will follow the surface. It works in both suction and in discharge. And at the heart of it is this preservation of momentum, which if you look at M1 and M2 in this equation, when the M's are the same, then we have very little mass transfer through collision. It's very similar to what happens with billiard balls. We think this is a better model for the code writers to consider. When all of the particles are the same, we're able to share that velocity much better. So in our response, we want to get real clear on what we're playing for. Removing all of the ducts as soon as we can, get that as number one priority. The next thing to look at is what are the other advantages that are available in the design. So, for example, can we ventilate this in such a way that we can preserve amenity so that near the discharge there is no local discharge CO readings that are high? Another one, and an advanced opportunity, is to look for natural ventilation. In this model here, we've got stairs that are a long way from the louvers, but if we open the stairs up properly, we can use them as extra fresh air turrets. And then down the bottom, you can see two sets of two reverse direction fans. In a tidal flow manner, they move air to work with the wind. And in doing so, we get these great CFD plots like you see here. Instead of needing 37,000 litres, we can ventilate this car park with 12,000 litres in suspended fans. The cost savings here were over 90% of the original mechanical budget for this space. At the heart of it, we need to have the HVAC brain be almost the same, if not the same, as the CFD brain. Whenever one of those two disciplines dominates, we do often end up with problems. The HVAC engineer appreciates what's required. The CFD engineer appreciates how it will be modelled. And so when we look at the CFD plot here, which is using basically colours to tell us what's going on, we can actually see the air. And you can see here that air is not moving like a tennis ball. But you get to test the design, and this is crucial. Testing the design helps us to be confident that the design we're promoting is valuable. We always test with the worst case hour to satisfy authorities. Another thing you need to test are the assumptions. So where the design relies upon natural ventilation, we need to test the different wind directions and ensure that under all conditions, we're achieving a very good outcome. In the screen here, basically the entire basement car park has got the same air quality as outside air. One of the other valuable things we can do here is use the variable speed drives associated with these fans to lower noise. So this is important because if we can remove attenuators and remove ductwork, then we can have very short and small discharges. By lowering the speed to 50%, we're achieving in the order of 12 to 18 dB reduction. We call this the silent night profile. So in all of these designs, whether we discharge at low level outside somebody's window or through a riser in the building if we have to, the silent night profile means that people can sleep. We don't have issues with acoustics. The advantages for your project, well, obviously, there's almost no ductwork, so coordination is much easier. We are over-ventilating, and yet there is no riser going to the roof. The air quantity we assume is based on the future vision of having 100% of our vehicles being EV vehicles. The air quality within the car park is much higher. We use something called the silent night profile to have a much quieter and simple array of discharges. The air quality is carefully controlled, so plant rooms and storage cages where we've got transient populations, they no longer need fresh air injection. We're saving time because the Met contract really just needs to get the cables in for the CO monitoring, and we're saving energy as the ductwork pressure is significantly reduced, and therefore the fan sizes can also be reduced. There are other advantages. The jump form no longer needs to house a car park exhaust riser. Our car parks are also much cleaner. So when we look at the car parks now, we see that there's virtually no ductwork involved in them. We can use natural ventilation to work much more, if you like, powerfully beside mechanical ventilation. There's almost nothing to install on the car park floor. We get to be very certain about the cost savings that are available. And this helps us with solving other builders' problems. Almost every project has builders' costs that the mechanical contractor won't appreciate. Penetrations, plant rooms, set downs and reroutes of hydraulics. And also the fairly difficult rules surrounding natural ventilation are now made much easier. We can ventilate in spaces that normally would not be considered. At the heart of this decision is that the ramps and ramp openings are now sort of supply outlets. They need to be perforated and holes allowed. Our car park discharges can be quite small little cabinets that almost are the size of a booster cabinet. And in those systems, we can discharge very close to the soffit or at the soffit without any intrusion within the basement car park itself. And these sorts of systems are around about 1 metre high. The air quality is so good that our proximity to air intakes can be satisfied. We want to demonstrate this to you. We often use CFD modelling to demonstrate this, and in this example, we've got a large loading dock that's been used in the worst case hour as a source of fresh air, and that fresh air bleeds in and dilutes large parts of the car park. We don't need a dedicated loading dock system, and we don't need dedicated miscellaneous ventilation systems. So our offer is simple, and it's obligation-free. Send us your plans, we'll do a mock-up design. If you like it, you can engage us. We can provide an indication of savings. And the value is significant. If you did engage us, the cost is typically in the order for large car parks, about $15,000. But the savings can be quite significant when you start considering the risers saved, plant room, construction time, attenuators deleted. Our guarantee is that we will save you at least 3 times our fee. So have a go and have a think about whether you could trial us on a project. We would take a set of plans like this on the right, and you can see here There's a supply air plenum across the top, and the peach duct runs everywhere. We would review that, but we notice that there are other parts of this car park that are actually unused. Step one is to delete the unnecessary things and get a sense of the cost savings achieved. So all of those red arrows pointing to ducts, we would delete it. The car park plant room, we would also delete. That could be repurposed for something else. The yellow plenum and the excavation of that, we would delete. And our design would look like this one on the right. Delete the extra excavation. Use that ramp in the middle as a fresh air supply. Down the bottom there's a red square. We may need a jet fan to help the circulation. And of course, extraction in that top left-hand corner. Once you've got these two systems, you can compare the results. What have we saved? What's it going to cost to build? What's the impact on the program? And this is where we get the opportunity to determine that we have value. And if you move early enough, then we can demonstrate its savings for other people's benefit. It's obligation free. One of the challenges, though, of course, for you is you're pretty busy. So let's talk about the risks. Obviously, most design managers have a lot going on. And you want to know, what can we do in the way of quality, cost, compliance, coordination, and of course, speed. These are all of the risks that a typical design manager is concerned about. I think we've addressed some of these, but let's continue. In this particular design, we have got the ability to delete lots of ductwork, but get an expert's advice in. You'll find that the cost for the expert is much going to improve the business return on investment compared to trying to do it yourself. All of those orange ducts there can be deleted, and the green ducts are the ones that already exist. And we get emails like this one, where basically people are caught by surprise. Geez, Rob, when can you start, sort of thing. What we have to do, though, is kind of capture this enthusiasm, but attempt to slow it down, because enthusiasm without thorough due diligence is also part of the problem. This here is the McClamey curve, and what it talks about is curve 4, where we do a lot of our design earlier on in the schematic design and develop design part of the process, and resolve our issues. In many ways, we are resolving the uncertainty surrounding the design. The sooner we can resolve that uncertainty, then the better it is that we are able to build what we need to build. So trying to resolve as many of those assumptions during the design phase before construction is important. Another risk that you face is the use of fan suppliers. Don't get me wrong, they are capable of CFD modeling, but they can often produce results like this one here, where air is blowing 60 and 80 meters almost effortlessly. Don't be fooled, air does not move like a tennis ball. This is an incorrect setting on the CFD machine. What air really moves like is like this model here. Now this uses FDS. So this is the same modeling software we use to model fire and CFDs. And what this does is gives us a much more accurate view of how the air moves. It helps us to document, and with good documentation, we're able to resolve the buildability illusion. Clash detection and integration is a stage in the process whereby the CFD should have been done and the design should have been done. And in this manner, the actual coordination certainty is closer to the perceived completeness of the design. And it should show up in our CAD details. So this detail below, where we've got like a booster cabinet, door assembly, and inside there are 2 fans that are in an acoustically lined shroud. Those sorts of details help people plan, where does power come from, what are the acoustic impacts. Another area that we need to be careful around is the actual movement of risers and discharge. What we see here is something called the Coanda plate. It's literally just a plate, carefully located against the wall, but it's a plate that sits 300 millimeters down below the bottom of a riser. So these sorts of details need to be factored into the documentation. And what we do find is we get these emails where, of course, people want penetration drawings first. That's simple to do with the teaspoon technique. We're able to be very clear about the sizes of those techniques. Another thing that we need to resolve in is the actual layout and where we're going to save this money. So sometimes people need to know where we're going to run large hydraulic pipes through the basement, getting that clear. Another issue is fire engineering. Fire engineers are often interested in whether the car park ventilation is affecting tenability. All of these issues mean that value engineering needs to be performed in places like the planning, schematic, and develop design phase, when the cost is minimal and the impact is significant. That's how we can locate discharges that are seemingly close to where people are. In this image, we've used the CFD to help guide where we're going. In this image, we've been able to model early so that we can dictate what happens to stairs and what happens to these car park vans. So test us, I beg you, on our next project, on your next project. We'll be able to provide a return on investment. There is an online calculator that's fairly straightforward, and it will tell you how much you'll spend versus how much you'll save. Most importantly, book an obligation-free review session. Send us your plans first, let us do some work, and then if you like it, go and use our online fee calculator at www.seedengineers.com. You can enter here that it's a car park, a new build, a number of floors. You can select a city in Australia or overseas. We now service many places in the US. And you don't need us to do the design work for these disciplines. You don't need us to help out, although whilst that's available, what I want to talk about today is just selecting the car park CFD study. And you will find on our online fee calculator that the price is relatively low cost for what you're getting. In this case, it's between $7,300 and $10,000. Now, what's the variation there? You might come back to us in a year. You simply put in your name and, of course, your contact details, and then you can choose what is the most important project outcome. You could also tell us what is the challenge that you most face. By providing us with that information, when we get together on a Calendly meeting, we're going to be highly informed and ready to go. Finally, when all of that data is entered into the online fee calculator, you get to choose whether you want just an email, just an indication, or do you want a formal fee proposal? There's a lot to keep your eye on. So to that extent, don't try to go it yourself. Go and use us to help you resolve everything from design and planning. If you like the way that this particular presentation works, have a look at our other ebooks and our other value management techniques.